And let's see where we are. Here we go. You should see my slides. Is that right?
Yes.
Okay, fine. So I would like today talk about arrays again, and especially the automatic resizing issue, and then some thoughts on RAM-ROM distinction. So let's see. This is the overview. I talked about data structures in the last meetings, in the tutorial part as well. And so the idea is to explain how you add the missing features, the missing features in Forth. And we will look into that shortly again and recapitulate how we define arrays in Forth and how we do this with implicitly within defining words and look at the simple arrays. Then I will talk about the bounds checking, and today's main topic would be the automatic resizing of Forth arrays, and hope we come close to that. And after that, I'm talking about a little bit about RAM-ROM and how you can strive to make portable programs that work on RAM-only systems or on RAM-ROM systems. So, yeah. So as a newcomer, you often hear or you recognize that Forth does not have a certain feature, X. So, and then you go ahead and ask, well, it doesn't have a case statement. You can use, you can define it on your own. Well, it doesn't have structures or it doesn't have arrays. Well, you can define arrays on your own. Yeah, depending on the application you choose, whatever is suitable. And the question really is, how do you do that? And that's the main topic of this tutorial section. So we look at these kinds of things. And the key feature is that you have to organize the memory in Forth yourself. What you get is exposed memory with addresses and read and write operators, which we call fetch and store. And so let's see, this is what it looks like. You can allocate some memory and you do this normally within the dictionary by means of the lot operator. And if you have a defining word, then you can use it to define new words, and that have array-like behavior. So you reserve memory for it, and then you define the behavior of the word. And what should an array word do? It should take an index, and it should return an address of the appropriate element within the array. And the way that create does works is that the start address, the parameter field address of the defined word is put on the stack. So actually when the does part starts, you have two elements on the stack, which is the, well, that's just the other way around. The index is at next of stack and the address is on top of stack. That's the reason why we have the swap here, so that we can do the appropriate address calculation, multiply the index by the size of the elements that you want to address, and then add up the base index, the base address of that thing. So SQ is actually on top when you start executing this, which means if you define an array like this, array will execute the create part, create the memory data structure here, and then define the word SQ that has the parameter field here and has the behavior to do the appropriate address calculation. So after that, you could probably, you can go ahead and store some parts. If you have the address of an element, you can store data in it. So you can say 16 for SQ store, SQ is an array, does the appropriate address calculation from its base address. Given the index, it calculates the address of the fourth element and gives you the address, so store can store the value 16 in there. So, and that's, if you don't need more, then you can go ahead, use this to do this. Even you can do address calculation on your own if your program doesn't want to use defining words or whatever, but we start from there here. So let's see. You can use the same interface, like define an array with a defining word, and then do also index checks. So if you use an index that is out of the area that you have been allocated for the array, then it might be nice if you get an error message or an exception is raised so that you can handle it in your program. And so we go ahead and define the array slightly in a different way. Now it has also some area where we store the size of the array. Yeah. So in the case of 6 array SQ, we store the size and then we allocate the appropriate elements, or space for the appropriate elements. And the behavior now goes ahead and fetches the length and checks whether you have a valid index. And if not, it throws, well, standard throw codes. It throws an error, invalid numeric argument. So you know, then if you use that, then of course in cell 4 you can still write the appropriate value, 16. But if you try to access element 6, then you get invalid numeric argument as it's out of bounds of where you are. Right, so that's one thing. And the typical way that we use to represent the arrays here is that we use the parameter field of the new defined word to store the data for all this, the elements and also the size. Yeah, but there's also the possibility to do it in a different way. So we did it like this, and we had this source code here. But we can also do it in a different way so that we do an indirection. So within the parameter field of the new defined word, SQ in our case, we have a pointer, the address, where the actual data starts. Yeah, and this has the advantage that we can change the address to some other area and update the pointer. So this could make a good place for additional features. And so then array changes a little bit because we need to allocate the appropriate memory, get hold of the address and store it in the parameter field of the new defined word, which means here we go ahead, take the number of cells that we want to allocate, we do the appropriate allocation, and this phrase actually leaves the address of the new memory on top, and then we store it in the appropriate thing. I'm used to use here where I say, okay, this is what has been allocated. The length is stored, and then the number of elements is allocated, and we get the address on top of the stack. And now we create the words and comma the appropriate thing, which creates the parameter field and stores the appropriate address here and the pointer in there. The behavior is nearly identical to what we have above, where we started with the index and the parameter field address, did the appropriate index check, and then did the appropriate calculation to with cell plus to get to the first element, and then do the appropriate address calculation. And here we do nearly the same, but because of the indirection, we need to fetch the address to get to the appropriate allocated data. Right. So that's one thing that we can do. We can split the place where we store the data from the word and have it allocated at some place. And this opens the possibility to resize our arrays. And if we look at the support for dynamic memory in Forth, then we have mainly three words, which is allocate, takes a number of bytes that you want to allocate and reserves that number of bytes in memory. How it does it, if it asks any operating system or if it manages this on your own, that's open. What you know is you get an address and some success indicator. 0 if everything is successful, or some throw code if something went wrong. And then there is free, where you can say, I no longer need memory. This can be reclaimed and can be used for later on. And if I free something, I get also a success indicator. And the third function, that third word that is especially interesting for us here is resize, which takes a memory address that have been allocated and a new size that we want to have. And it makes sure that the reserved memory either shrinks or grows and returns the address where the data now is, and also a success indicator. So this grows or shrinks, and it might be that the memory management is not able to allocate to just resize in place. So it needs to allocate a new larger block, and then all the content of the existing memory needs to be copied over, and resize guarantees that this is the case. So it preserves the content of the resized block. Although it might not stay at the same address, the content will be the same before resize is called and afterwards. But maybe it allocates a larger block if necessary, copies over the old data, and gives you the new address and a success indicator whether this all has been worked out fine or not. So that's the fourth way we have dynamic memory, similar to C alloc function calls. And with this, we can go ahead and do a very similar thing. So we still create the same data structure as with the resizing, with the bounce checking array. But instead of throwing an error in with every index that is out of bounds, we only throw an error if the index is below 0, because then it's obviously somewhere where we don't want to address memory. But if it's large, then we extend the array appropriately. So the index will actually fit in the memory, and then we have a larger array and we can store the appropriate values. So, and we do this by invoking this fit word here, and fit makes sure it gets the index and the array address on the array address here on the stack, and makes sure that the index fits inside the array, increasing the array until this fits, and that you could have different strategies to do that. And one very clever strategy is to double the size of the array until it fits. And then normally you have something that is good enough for many other indices that you might want to use to store things. So again, we define an array, now a resizing array called SQ. It has the same interface. So you give it an index and it returns an address, and you can store values there. So 16 for SQ still works, nothing happens. We do this under flow check. It's not triggered, and fit will just say, well, 4 is good enough for our array. We can return the address, and store can actually put the value in there. But if we access element 31, then that's actually not inside the valid array that we currently have, because it's only 6 elements large. So fit will increase the array. We'll see, 12 is not sufficient. We'll increase it again. 24 is not sufficient. Increase it again. 48, yeah, that's fine. 31 fits within 48. And so increase or double the size of the array 3 times, and then returns an appropriate address, preserving the content that the array already has. And then you can store 961, the square of 31, in that. Yeah, so let's see how fit will work. It will actually try to compare that everything's that the index matches the size of the array, and if not, it will invoke double, and double will go ahead and call the appropriate resize. Yeah, and resize, so it doubles here 2 times. It doubles the size that we have. If the resize is successful, then it stores the new length at the beginning of that block. And so you can call double again. So if you access the array with 31, 6 is not enough, 12, 24, 48 is what we get. And the memory is enlarged so that we have 31, where we can store 961 later on, and it goes up to 47 because the size is 48. So that's rather nice. And let's see, I think that's a good place to have a look at the demo. So here is again the source code that I just presented, with the addition that I'm outputting something when we invoke double. And so we defined our array SQ with that. We stored 4 in there, so we can say 4 SQ fetch dot. Yeah, not surprising, there's 16 in there. And now let's see, we can say 961 31 SQ, and I'm not doing the store right now because we want to inspect what's on the stack afterwards. And we say this, and it says double, double, double. And so let's see what's on the stack. It's an address and the 961 that we had, and I can say store here. So let's see, what is the size of the array that we have? So we tick SQ, go to its parameter field, fetch the address of the memory area that we manage, and then we fetch the size of the allocated block, and ta-da, it's 48. Great. So that works fine. And so what we have here is the parameter field has a pointer to some data, and we can change that data very easily to contain different things. We can change its size if it's managed data. And this made me think of, well, maybe this has something to do with RAM and ROM. And a very similar structure that we have is if we look at RAM-ROM systems. So if you look at Forth systems, there are, with the idea of using flash or ROM or RAM, there are 2 flavors mainly. It's the RAM-only systems, those systems that just have a single dictionary and manage all the operators in this, all the memory in the same way. All words operate on RAM. So if you allot something, or if you allocate something, if you comma or whatever, then it's all in the same memory area. There's here that points to the free available space and so on. And then there are RAM-ROM systems that also have flash. It could be that you just have program storage in ROM, but it could also be that you want to have some data there. And this is my concern here. So a good distinction, some Forth systems do it, is that they say a lot and here actually work on RAM part of the memory, and comma and C comma, where you want to build up tables, for example, they work on ROM. And then the question is, can you write definitions that will work on RAM-ROM systems, although you don't know actually how they do it, assuming that they use a lot and here for RAM and comma and C comma for ROM. My claim is if you want portability on RAM-ROM systems and RAM-only systems, you assume that you have a RAM-ROM system and include the indirection that we've seen, then the definitions will run on both systems. So a typical word that shows, or a simple word that shows this behavior is the word buffer colon, which allocates a buffer, very similar to what we have with an array, only that it doesn't do the address calculation on its own, but it just returns the base address of the allocated memory. So a most simple form is create a lot. And there's a lot of debate why you would have buffer colon if you could just write create a lot. And here is my take on that. So you can use it in RAM-ROM system as well. Then if you have an indirection, buffer colon will actually, in its parameter field, will have a pointer, the address of the buffer, which might not be changeable because it's in ROM, but it points to a RAM area that you can use for storing the data in the buffer, which is a pattern that is very similar to what we have with the indirect array. So we do here swap a lot, leaves us the address in RAM on the stack and allocates the amount of U bytes. I use these kinds of structure pictures to describe how the memory is organized and how it's separated. And then we do create comma and store the pointer to RAM in the parameter field, and assuming code and the parameter fields of words go in flash or ROM, you can't change it later on, but it points to appropriate region in memory. And now you need to do the indirection. Here create will just return the address of the parameter field, and here you need to actually fetch the pointer to get the address of the RAM. Yeah. And so if you look at this, both definitions will work on a RAM-only system. Only this one looks strange because it has this indirection that you don't know why it is, but now you know. The bottom definition actually works in RAM-ROM systems as well. Yeah, that follow this convention. So I started to do defining words when I know there is also the chance that this need to run on a RAM-ROM system. I started to define words like this. Yeah, maybe I start with the bottom, with the top one, and then I said, well, I have a good pattern of how to move to the other way. Okay, so that's what I wanted to talk about today. So automatically resizing Forth array, making use of Forth built-in memory management. So if you don't have resize, allocate, and free in your system, then that's probably something that you need to add if your application requires this kind of features. Yeah, I talked a little bit of RAM-only and RAM-ROM systems and how to write definitions that are likely to work on both systems. If we look at the whole sequence of things that we looked at, we can make another check mark on automatic resizing and RAM-ROM systems. So we talked about structs, arrays, and now the resizing things in enumeration types last time, which leaves us open with objects, something that is a great topic for 2022. Thank you very much for listening, and I'm open for any questions.
Wonderful, Ulrich. Excellent.
Okay. Yeah. Other questions?
Guess what? I have a question.
Sure. Yeah.
You covered most of the data structures, but the question I have now is, which one is good for what?
I see. Yeah. So yeah,
frequently I don't know what to choose.
Yeah. So it's mainly if you have names for different parts of your the data that you want to store. Is struct is probably the fine thing. You give names for certain parts, and if you just have a sequence of things, then an array is appropriate. And you could, of course, you could nest this. So if you have some records and you want to have an array of records, then the appropriate size of the things that you store in there is different, and you have to do the address calculation a little bit different. Yeah, but that's mainly what it is. So if it repeats, then an array is the appropriate thing. And if it's different parts that are also of different quality that belong together, then a struct is the appropriate thing. Yeah, and then in doubt, think about one or the other and ask yourself the question: do I need more of them? And then an array is probably good. Or does this have some kind of structure? Is it primitive, or is it composed of different things? And then a record might be the right thing. Yeah, and then you try out.
I didn't get exactly the difference between structure and enum.
Enum is just a name for different values. So it's not a so you name in principle atomic values like states in the state machine or colors or weekdays, and there's no further structure involved there. You just give names to distinct values, and that's what an enum is for. So you don't need to write magic numbers in your source code, but you can just use the names.
I have a question, but maybe it's not such a question. When I saw 6 and SQ, and then you go enter to see the result.
Yeah.
I thought that it's the same that you had a word that calculates the square of the number. So this array that extends itself should be seen like a memoization. So you can pre-calculate some many values. Is the same, or it's feasible?
Yeah, that's of course that's possible. You could either think of calculating things up front when you load things, then so that you build up the table, or it could memoize this. And of course, the running example is just a table of square roots, and you need to fill it. Yeah,
you're right.
Yeah, but of course, a memoizing that array would also be fine. Maybe you have to supply the formula to calculate the values as well. But yeah.
Every time I listen to you, Ulrich, you give me very good idea.
Okay, and thank you.
It's the third time, I think.
Yeah, thank you very much. Yeah, I encourage everyone to experiment with this. So go ahead and try things out. As you see, the simple interface, you have a word that takes an index and returns an address that you can later work on. Can have lots of magic inside. So like resizing and checking the index, or resizing the area appropriately to satisfy what the user need is. Yeah. Of course, if you have a program that runs nuts and says 1,000,000 SQ, then it would extend this a lot. Let's see what the Forth system actually does here. I'm curious now. Let's see. So if I have a 1,000,000, well, that's 1,000,000 SQ. Yep. Wow, this does it. So very nice. And let's see what SQ actually, what size it actually has. 1,500,864 elements. Yeah. So, but of course, I probably can kill it. No, this is the issue with these modern computers. They have so much memory. Yeah, anyway. Are there any other questions? So Dimitri,
I have a question.
yeah, okay, please.
So, well, one question and one comment. So normally in Forth, right? Because when I was learning, I kind of learned that the simplest array is use create and then you allot how much memory you need. Are you saying that and you can't necessarily comment on all Forth systems, but if you try to access something outside of the memory you allotted, would the Forth system normally allow it, or wouldn't you have an out of bounds thing?
No, not the normal thing. If you use the first definition that I gave, which just does the address calculation, you just access memory outside this. If you fetch, well, then normally this doesn't have a negative effect. If you store their values there, then you override something, probably, depending on the Forth system, other data or even code, or well, maybe worse, the link the link address of some word, and then your dictionary is corrupted. The next time you do words, the system will crash. Or so that's I think my main statement is you do whatever is appropriate for your application. So if during development you need bounds checking, then you use the bounds checking version of the array. It has the same interface than the normal one. And then either you omit this or you keep it in the application code. But if you're confident that all array accesses are fine, then you can just use the simple one. And if you don't know upfront how large the array indexes are, then the resizing array might be appropriate. Maybe you put in some upper limit, so that if you say 100 million is the index, it will still throw some, that's out of bounds. We don't want to support that. But it would just resize appropriately. And so if your application need is like that, then go for it.
I see. You have both answered my question and gave my comment, because I was going to comment and say exactly what you said, which is, you implement what you need. And I actually quite like this about Forth, although it was strange at first. Why don't you have all these things built in? But you can design them to suit your application. And I found many cases you don't need the overhead that normally comes with, say, structs and arrays. You just need things that are stored in next to each other, or things that, I don't know, they're stored in a pattern that you can remember, or you have words to access. So I agree with that. That's it from me.
Yeah, actually, so that's the idea of the project Forth.works, where we collect ideas. So you need to, of course, you need to have your tool set. You need to know what to do to achieve a certain effect, and that's what the project Forth.works is about. Collect these ideas and write down so that you can go there, consult the idea, and say, well, this is what I need for the application right now, so I can incorporate this and define the structures and the words that are necessary to support what I need. Right.